textbook, and you want to look at other references, and you want to see state-of-the-art applications, all these kind of things. All right. So that is the plan for the project B. Okay, so we have two problems, and I even did not bring the problem statement. Any of you have the problem statement for homework 3? Appreciate if I can borrow that. No one has it?
POSAR problems?
Problem
Or-
homework 3?
Yeah, these are the
Okay.
POSAR ones, and I have the ones that you wrote too.
Yeah, that's the one. I need the one that I.
Okay, here.
Okay, these are the ones. Thank you. Okay, the source is a 5 millivolts. Operating at 12 megahertz. Connected to port 2 of this device, the load is 100 ohms. And this one is 50 ohms. The source is 50 ohms. This problem here actually comes from radio engineering when I taught that a few years back. But the concept is the same, whether it's in the microwave or the RF frequency band, the S parameters issues are the same. Reduce the network S parameter equivalent signal flow graph. So obviously I have a signal flow graph for the device. Okay. And I have a signal flow graph for the source and a signal flow graph for the load. Now, depending on the direction of arrows, all right, we can reverse those arrows kind of thing here. So if I call this A2, because that's port 2, this is A1, all right? So this is B2, I'm sorry, B1, and this is B2. So obviously I'm going to call this here BS, I'm sorry. BS would be the arrow going in here. Now, we have to distinguish between signals and S parameters. The signal is the power flow, while the S parameters is the ratio between signals. So the S parameters is like the gain or the attenuation, whichever way you want to look at it. It's basically gain, all right? So the ratios are the S parameters. I'm going to label those in white. So this one here is S12. This one here is S21. This one here is S22. This one here is S11 of the device. This one here is gamma of the load, which is S11 of the load. This one here is gamma of the source. And this one here is 1. There's nothing here. There's no multiplier here. So the white are the multipliers. Now, number-wise, we have 1 is minus 0.3, so this one here is minus 0.3. 2 is minus 0.1, so this one here is minus 0.1. And then 2 is 0, so this one here is 0. And 2 is J.7, J.7. We'll choose our reference. The problem did not state any reference for us. No, it did. Okay, these are 50 ohm S parameters. So this has to be done with respect to 50. This will have to be done with respect to 50. So this one obviously is 0. And this one here is 100 minus 50 divided by 150, which gives you 1/3. Right? So that's the first part. Determine BS, B1, B2, and Zn. All right? BS, how much is BS? I don't remember if I gave you an equation for that or not before. I did not. Okay. So let's work this one out on the side here. BS, ZS, I want to convert that to gamma S and BS. Well, basically we say these equivalent to each other. If they are equivalent to each other, then they will be equivalent under all circumstances. The easiest way to do it is to say, okay, if I were to connect a matching load here, Z0, then I would connect here a 0, right? That's matching. Then the signal here will be related to the voltage here and the current here, V and I. All right? Well, we know the relationship between A and B. A is equal to what? V plus I times Z0 divided by 2 square root of Z0, right? And the B is V minus I Z0 divided by 2 square root of Z0. In this case here, V is equal to Vs, I'm sorry, that's Vs, times Z0 divided by Z0 plus Zs, and I is equal to V over Z0. The signal at this location here is actually your A. that is going into the load. So that is the sum of these two. So V plus I Z naught, that means 2V divided by 2 square root of Z naught. So your A here is equal to obviously BS divided by 1 minus the loop gain, which is 0. So it's equal to BS. So in this case, the BS is equal to this A, which is 2V divided by 2 square root of Z naught is equal to Vs Z naught divided by Z naught or Zs square root of Z naught. So you can get your BS based on that.
How'd you get the A is equal to BS over 1 minus 0 equation?
The A is equal to BS divided by 1 minus the loop gain, right?
Okay.
And the loop gain is 0 times gamma S,
Okay.
which is 0. So it's actually Vs square root of Zs square root of Z naught divided by Z naught plus Zs. In this case here, since Zs is equal to Z naught, or Bs, I'm going to use yellow here, I'm sorry. Is equal to Vs times or divided by 2 square root of Z naught.
What's interesting?
Hmm?
What's that interesting? What are you showing here?
I'm just getting the BS using this equation. Since Cs is equal to Z naught, we have 2 Z naught here, and the square root of Z naught cancels out. So that is the expression for BS. So now we have numeric values for everything. We want to find B1 and B2 and Zn. We'd like to find B1 and B2. So what I'm going to do next is redo the diagram without the zeros. Right? Was a 0 here and 0 there. So obviously that's B2, and the signal here is actually B1. And this is BS. I'm just going to maintain the labels here so the numbers will not confuse us. Can anyone argue with me about B2 is equal to BS times S22? Any doubt about this? Straightforward. B1 is also straightforward, that's BS times S12, come to here, divided by 1 minus loop gain. Next is to find the input. The input would be the impedance seen at this point. So I'd like to reduce the network to an S parameter at this location. Well, obviously, this whole thing here does not feed back. We kill the feedback. So as far as this is concerned, we only see S11. Gamma input is equal to S11, and therefore Z input is equal to S22, my apologies. Thank you. It's backwards. Whenever you're working backwards, opposite to the convention or different from the convention, you have to be extra careful, which I did not do. All right. The third part is determine the power out delivered to the load. So we need to find the power delivered to the load here. Well, if we look at the load, the B1 is going in, A1 is coming back. This is going to the load, and this is coming back. So the P load is equal to B1 magnitude squared minus A1 magnitude squared. Whatever went in minus whatever got reflected. Yeah, okay, I have the B1 here, okay. My apologies. All right, how much is A1? Gamma L times B1, all right. Just put the space here. So I'll work out the A1 is equal to gamma L times A1, times B1. So that's equal to BS S12 blah 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 S11 gamma L magnitude squared minus 1 minus gamma L magnitude squared. Questions? Move on to problem. The last problem, which is actually problem 4, not problem 5, because I dropped one of the proposal problems. See how neat the S parameters are? signal flow graph. If you're working this problem with typical circuit theory with impedances, you'll discover that you'll have to do more work and more complicated equations. Next problem, there are two parts. One of them is we would like to get an expression for S21 of a combination of two networks. One of them is a three-port network. And the other one is a two-port network. If you want to see the circuit, there are wires here. And these wires are connected to each other. So the combination network is going to be like this, and will only have 3 ports. So we'll call this device A, call this device B, call this 1A, call this 2A, this is device 1B, and that's port 2B, and this is port 3A. We're not dealing with wires or connectors or conductors, we're going to do S parameters. So I'm going to do arrows now. So there will be A1A, B1A, B2A, A2A, and this one here we have A1B and B1B and B2B and A2B. And this one here, it doesn't matter which is which. There will be a B 3A and A3A. So these two here, you will have B2A is equal to A1B, and A2A is equal to B1B. You have two options. One of them is to write the equations. Like for device A, you write B1, B2, B3, A is equal to S parameters here, SA, A1, A2, A3, A. The second matrix will be B1, B2, B3 is equal to SB, A, B. And then use this plus that. And reduce all to the following. Again, B is here, A is here, but this one here will have A1A, B1, I'm sorry, B1A, B2B, and B3A in terms of A1A, A2B, and A3A. That's what you need to do. Manipulate those into this, and what you get here is S composite.
Is that B1?
What did I do?
The first one?
This one here?
No, that,
Here?
yeah.
It should be B1A, you're right. Thank you. Now, obviously, that's the tedious way, but the systematic way, right? This is how systematic it can go. Just sit down and manipulate the equations and reduce it to that, because these are going to disappear. The A2A is going to disappear, and the B1B and the A1B and the B2A. These are going to disappear from your equations, and the remainder will reduce them. Now, the smarter way is to work out the signal flow graph. This one leads to a B, this one leads to a B, this one leads to a B. Labels: S11A, S12A, S2, missing S33 here. S21A, S22A, S21B, S22B, S21B, S12B, and S31A, S32A. This one here is S13A, and this one here is S23A, S33A. How do we get that? We go back to this line here. This is the final form. So what do? I just take them one at a time. I kill A2A, I kill A2B and A3A. I kill A3A and A2B. And leave A1A. In this case, I can get this column. So this column is going to disappear, 0 here and 0 there, these two columns are going to disappear. The 2 zeros here, kill those two. Just keep that column. What's this column composed of? S11 composite, S21 composite, S31 composite. So S11 composite, S21 composite, S31 composite. That's equal to B1A over A1A. This one here is B2B over A1A. This one here is B3A over A1A, with the condition of the A2 and the A3 being zeros. A2 composite and A3 composite is equal to 0. So next, I erase the lines coming out of this. I'm gonna dash them. That line is gone. And this is 0, it means this line is gone, this line is gone. Also, this line is gone off of that. So the final diagram. Right? S21B, S21A, S31A, S32A, S12A, S11B. S11B, S22A. These are actual composites now, okay? Same thing. I relabel them to composites, so they are composites. Let's see if we can write them by inspection. S11C is equal to S11A plus, right? This path plus. This one doesn't lead anywhere, right? This one goes, loops, and comes back. S21A S11B, S12A. That's your loop. And the loop has a feedback loop inside it. So let's divide it by 1 minus the loop gain in the feedback loop, which is S22A and S11B. You have two paths here. Let me draw it separately here. So you have the sum here. That's the summing node. This path plus this path. This path is right there, separate, and the other one is the loop, divided by 1 minus the loop gain. That's 2-1 composite. I'm going from here to there. Can you check after me and see if there are any other patterns that I forgot? That's the only path you've got going from A1 to B2. That's 3-1 composite. I'm going from 1 to 3. All right? So I have an S31A plus, right? S21A, S11B, this one times that, divided by 1 minus loop gain. S